So just to remind you guys, there's the sheet that's up on Canvas, 5.3 through 5.6 practice. We did a few of these before. I've got the answer key up, like the solution video. This is pretty much, I mean, you know, like number 1 and number 4 are not going to be on the quiz on Thursday because that's from earlier. So the quiz is going to focus on 5.4, 5.5, 5.6. So like Descartes' rule and bounds and, you know, there's going to be another problem where you have to do all this stuff, but you're going to start with it not factored yet. And then you have to factor it, and then you still have to do this stuff here. And then, of course, there's going to be at least one of these to graph. All right. Is that all right? Do you guys have any questions from homework or anything? What do I have? I have 13, lucky number 13 people. So I'm only missing about 27 people. No, 17 people. I thought for a minute it was worse than it was. Do you guys have any questions from anything? Any homework questions? Any general questions? Any how do you find asymptotes kind of question? No? Yeah, everything's great. Everything's good. I love you guys. I don't know. Hopefully you understand that I love questions. I don't understand. I don't know if you guys think I hate them. I don't know if I give that vibe somehow. I live off of questions. If you never ask anything, I have no idea what you don't understand, right? Nothing. Nobody wants to go over everything, anything, nothing. Everybody's ready for the quiz. I could give it right now and you all would be good. Is that what you're saying?
I guess I've got a question.
Okay.
Could you not?
Could I not what? Give it
give the quiz right now?
Yeah, I won't. I'm just trying to get some kind of reaction out of people. Yeah, it's difficult enough. I understand it's got to be difficult. Obviously, it's difficult for students online. It's also very difficult for teachers online. In a classroom, I could read people's faces a lot better. And I could see if I do a problem, I look around, I'm like, well, they obviously don't have a clue what I just did. Here, I don't even have that. So I really hope that I always try. I don't know. I think I have a natural ability to be easily accessible, I think. Like I'm saying, I really hope I'm not like shutting you guys down somehow. I really hope I'm not doing something subconsciously to shut you guys down. We need to be able to ask questions. If I ever make anybody feel bad about asking a question, you got to call me out immediately because that's the last thing I want to do. So see, I got a question. Somebody's asking something just so I'd shut up. I understand. I appreciate that. Why did I close the book? That was smart. So 5.5, number 42. What do you do if you encounter problems that don't factor out? Now see, here we go. I love it. Let me do that next. Hold on. I need to ask you what the hell you mean, but we'll do that next. So 5.5. Oh, I think I know what you mean. Okay, this is a good question. So let's look at 5.5 first. Number 42. Check. All right, so this one asks you to find all complex solutions. So that just means find all the real stuff and the imaginary stuff. This one's a cubic, and I want you guys to start to realize that once you get down to quadratic, everything becomes much easier. And I'm going to answer the other question in the chat right now. In fact, let's do this problem. Let's do this problem. Why not? I'm all excited that I got a question. I'm happy. So let's ride the wave with Jeff and let's just do this freaking problem. So can somebody help me out? Make a list of possible rational roots and just overlook my horrible writing. How do I make a list of possible rational roots? What's nice in this problem? What are we, sorry?
There should be positive.
Oh, okay, okay. So we could also look at Descartes' rule. I like it, right? Even if they don't ask you to. This problem says nothing about Descartes' rule, correct? But we know Descartes' rule. Why not use it? So what did Rio notice? Somebody else tell me. What did Rio notice about the original function?
It's all positive.
It's all positive. I love it. So that means, so then there's no sign changes. So therefore there's 0 positive roots. So instead of putting plus minus in front of my list, I can just put negative. Do I have to worry about making ratios in my list of possible rational roots? Do I divide by stuff? What part of this tells me I don't have to do that? Does anyone understand what I'm saying? Let me see.
The lead coefficient is 1.
Yeah, there you go. Somebody else got it. Cool. And you got it. Everybody got it. So that's a 1. So I would divide by all the factors of 1, which is 1. So I won't change anything. So all I need are the factors of 85. All right, so that should be pretty obviously 1. 5's got to go into that bad boy. Something and 85.
17.
Yeah, there you go. 5 times 17. So that's a relatively nice, you're like, thank God. You love numbers now that you can't factor too much. Now, let me really make a point. Is everybody cool with what's happened so far? Even if you didn't think about Descartes, you're fine. You don't have to, but it's just the thing that if you notice that they're all positive, for example, then you know Descartes is going to help you out a lot. Okay, so anybody have any question with what's happened so far? Okay, now, I really want to make a point out of this. Are these all the possible zeros that could happen?
No,
Why not?
there should be complex, or there might be.
All right, there might be complex, or what other kind of answer could there be?
Undefined.
No, stop, no. There's got to be 3 zeros. So you could have, one of these could be a 0, or you could have a complex 0, or what?
Imaginary.
Nope, that's complex. There we go. Somebody's got it in the chat. Irrational. So be really, really careful. I saw a few things people writing in the homework that told me you didn't quite understand. This list is not a complete list. These are the nice possible answers. And then you got all the gross answers you could get, right? Okay, maybe. So this is going to lead into the other question from chat. So a few people have already done this problem. What did anybody get? What something that works? Why is my? I don't know. I'm not sure why it's doing that. Okay. So let's try one. So let's try -1. Yeah, this is weird. Why did that suddenly become so thin? I have no idea. So I'm going to put 1, 13, 57, 85. Right, so I'm going to try -1. I can pretty much quickly see this is never going to work. So I put 1, -1, 12, -12, 35, -30. Okay, that's not going to work. Right? Okay. And notice something though, screw it. That's not going to work, but it's a negative number, so it can't be in upper bounds. So I'm not even going to say anything there. Okay. What do you want to try next?
-5.
Okay, this makes sense. We'll just go through the list. So you guys go ahead and do this real quick. I'll sit here, and if you've already done this problem, just sit there with me. If you haven't done this problem yet, real quick, try to do synthetic division with -5. Here we go. Interesting. Okay. All right, I'm going to catch up with you guys. Does -5 work? Looks like it does. I like it. So how have I factored this so far?
X plus 5.
Good. And it was x cubed, so this is now going to be
X squared.
and this is the question from chat, because this is really, I'm trying to solve this equation here. And somebody in chat said, what do you do if you encounter problems that don't factor out? So just to be clear, do you mean something like this, Kirk? Like that doesn't factor, right? There's no factors of 17 that add up to be 8. It just ain't gonna happen, right? Don't ask me why I said it like that. I have no idea. Like the whole question, what do you mean? I'm sorry. I don't think there's any problem they gave you where nothing works at all. So if you think that's true, yeah. Okay. So what I thought was you meant, what if I get to a point like this? Because some people in the homework didn't continue with this. They just made the list of answers. They just said -5 and that's it. But this has answers also, of course, right? In fact, I know, especially because they said this, I have to get 3 answers, don't I? I have to get 3 answers. So of course, I'm just going to use quadratic formula on that. And I'm not even going to do it. I don't care. You guys just do that. All right, so use quadratic to finish this out. -b plus or minus blah, blah, blah. Is that okay, guys? Is that all right?
How did you know there would be 3 answers?
Can anybody help me out with that? How did I know?
Because of degree.
Yeah, the 3rd degree. What does that come from?
Multiplication?
It comes from the fundamental theorem of algebra, FTOA. Right? So fundamental theorem of algebra says, whatever your degree is, it must have that many x-intercepts. Some of them could be repeated. Some of them could be complex. Some of them can be real, but it must have that many x-intercepts.
Okay.
What is somebody else? Let me see. Hold on. Shoot, I lost my. I'm going to take this away. Here we go. 57. This one here. So some people were having some trouble with this, but how do I set up the list of possible rational zeros? I have to take into account what parts of this. What parts of that are going to create this list for me? I don't know. Is that a weird question? Do I care about the 3, for example?
No.
What do I care about?
The lead coefficient and the constant.
Yes. I like it. So then the list of possible rational zeros. I would put plus or minus. And on the top, I put factors of 5. And on the bottom, I put factors of 2. Now, I mean, I showed you why that is true. We discussed why doing that makes sense. So there's 2 layers here. You got to remember that's how you put them together. The factors of the last number divided by the factors of the first number, all the different combinations. But it would be great if you also remembered, at least remember there's a reason why that's true, right? We did discuss it. We discussed why that makes sense, why it must be that. All right. So that your brain can remember it better instead of just going, well, this is shit some dude made up over the internet. I don't even know if he's my teacher. It could have just been somebody. My teacher might be in his closet. He might have Oh shit! Now somebody's gonna check it out. I'm in the closet. Somebody's in the closet. All right, sorry. So the factors of 5 are 1 and 5. The factors of 2 are 1 and 2. I don't know why I have so many pluses and minuses. So then you make all the possible. So 1 over 1, 5 over 1, 1 over 2, 5 over 2. There is your complete list of the possible rational zeros. You guys with me out there? Okay. I'll take that as, yes, yes. Oh, sorry. Whoa. I just got a ton of massive dump of texts here, chat. 2 and 5, factors of 5 divided by factor. Okay, okay. I thought I needed to factor it out. Oh, be sure. Yeah, some of you guys just please read the directions. Some of you guys are doing too little, and then some of you guys are doing way too much. All this wants is that, and you're done. That's all it wanted. That's all it wants. Poor little problem. And then you start tearing it apart. He's like, no, don't tear me apart. He just wants this. He just wants that list, right? Okay. So do please read the directions. And earlier, some of you guys were just making the list and then not finding the actual zeros. And I'm like, well, that's what they asked you to do. They want you to find the actual zeros. Don't just make the list. You got to keep going. This one just wants the list just because. Okay. Did I miss anybody else? All right. Any other questions, guys?
Yes.
Yes.
So could you go over number 54, please? Yes.
Okay, so 54, it says Descartes' rule. And we talked about this in class. They don't have a given graph, right? So what they want you to do is just to plot this on Desmos or your graphing calculator and just say something. So Descartes' rule is going to say something like 2 or no positive real roots, right? So if you graph it and you see 2 positive roots, say 2 roots like Descartes was going to say, or just, make a connection there. That's the whole point.
I think I got it. Thank you.
Okay. So there's not a ton of work here to do. You do Descartes, you look at the function, you look at f of negative x to see the negative possibilities. And then you look at the graph. You just graph it on Desmos or something and you say, did Descartes accurately predict what was going to happen? And of course it will. A few people are writing down like 3 positive, but what's wrong with just saying 3 positive? What's wrong with that? If somebody just says 3 positive, that's what Descartes says. What's wrong with that?
It could also be 1 with 2 irrational. Yeah.
And why do you always go down by 2?
Because they kill each other off.
Because complex answers always show up in complex conjugate pairs. I don't know. Do you guys, we talked about that a few times. I don't know. Complex answers come from quadratic formula basically with plus or minus. And when this part is negative, you get a complex answer. So they're always going to show up in pairs. So if it's not 3 real, if there's any complex, there's going to be 2 complex. So if it's like 3 possible positive ones or 1 possible positive one, because if you lose one to being complex, you got to lose 2 because they come in pairs. All right, I like it. I have no idea why this means pair to me. I don't know. Right? You guys with me? Everybody all right? All right. Anything else, guys? Anything else? So we do still have a quiz happening Thursday. And just in case you missed what I said earlier, I got to make this all about me. It's going to basically be 5, 4, 5, 5, 5, 6. I'm not really concerned about 5, 7 that much. It's stuff we've already talked about before. And to be honest, the thing I showed you with the number line, they actually ask you to do it in a graphing calculator, which is kind of dumb. The number line thing is actually a little easier, to be honest. I don't know if you guys remember what I'm talking about. Finding the domain, you find the zeros and where it's undefined, you make a number line and you can see where it's negative and positive and you can answer the question like that. That was the only thing I really focused on in 5.7 because it is an interesting thing that you're going to use again in calculus. Okay. All right, so if there's no other questions, we'll just get back into chapter 6. I think the last thing we did, yeah, it's funny. The last thing we did, we actually did 6.1 and 6.2. So we talked about exponential functions, right? So we came up with this idea of exponential growth versus linear growth. Exponential is just insane growth. It goes very quickly. We talked about the basic look of exponential functions. We talked about what's happening at the x-axis.
It's an
What is that?
asymptote.
Asymptote. I love it. Blah, blah, blah. There could be a number out front. And this is a really good place to talk about this. So be really careful about if I saw this, I have a few too many people tell me that that equals 6 to the x. Is that true?
Nope.
Now I kind of gave it away with the way I asked that, but can somebody tell me right here, how many 2s are there?
One.
There's 1 2. And how many 3s are there?
X.
So how could you make x 6s when you have x 3s and only 1 2? That's one way to look at that. Do you guys see that? Now, a much more straightforward way to look at it is freaking PEMDAS, right? You've got to do exponents before you can do multiplication. So you can't just make that 6. You guys with me? So what effect would this have? Let me rewrite this because I got a lot of shit happening up there. If I have this function versus this function, we all know, Jeff, I swear to God. Hold on. Make it an exponent, buddy. You could do it. All right. There we go. There you go. Okay. We know what effect this would have. What effect will it have compared to this?
Stretch.
Stretch. So it'll be a vertical stretch. It just doubles all the outputs, right? So let's see. Let's see if you guys remember this. All right. Can somebody tell me the anchor points that I use to do like a base function? Does anyone remember what the anchor points are?
-1 and 0 and 1.
That's right. That's right. Oliver Twist person. So I use these because they are the easiest things to use. If I have 3 to the x, 3 to the first power is 3. 3 to the 0 power is 1, and 3 to the -1 is 1/3. And then I can just move those around. So I call those my anchor points because it anchors my original function, but now I can just pick the anchor up and move it somewhere. Does that make sense? Does that not make sense to somebody? Let me know. So this is the original base function. And now what am I going to do with every point? I'm just going to
Stretch.
I'm just gonna double, right? So let me change my color here. So this point right here is currently got an output of 1. So of course it's going to become an output of 2. This has got an output of 3. So it's going to become an output of 6. This has got an output of 1/3 right here, right? So now it's going to have an output of 2/3. Whoa. So now my function's going to do this. It's just going to grow faster. Okay, it still has this asymptote here. All right. Why didn't the asymptote move?
It's always 0.
Well, unless what's there? What kind of shift was not there? That would
Reflection.
make it. No.
Horizontal shift.
No.
A constant, so like the y.
Vertical shift. I like it. Because imagine if I had an infinite, if this pen was infinitely long Would it matter if I shifted it left or right? No. But if I moved it up or down, now that makes a difference. So if it's infinitely long, I couldn't even tell a left and right. It wouldn't mean anything to me. But if I moved it up or down, that would, holy shit, that infinite thing just went up and down. All right, that I would notice. I don't know. Does everybody understand that? So, okay. All right. Okay. Let me clear this away. Bam. So that's why they say this is the general look is it could have an A out front. And it's really I don't care about that. It's the next section that deals with graphing these things. So the homework you're going to see in chapter 6. Let me see where things get interesting. Blah, 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 blah. Oh, let's look at this. This is where things get interesting. Well, this isn't so interesting. They give you the function here. Yeah, here we go. Okay. So you guys know how to create a linear model if I give you 2 points. What does that mean? If I give you 2 points, you can find the slope and then figure out the equation of the line. Correct? You should be like, please give me that problem on the next quiz, Jeff. Please, dear God. So what this is talking about is, how do I create an exponential model given 2 data points? So let's try a problem out. Let's look at this problem. So in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. And they tell me it was growing exponentially. Okay, so what we do is we start with our form of our function, right? A times b to the x. Do they give me, depending on how I define my variables, how can I define my variables? What am I going to let t represent? What's the best thing to let t represent? Let's see if we've done enough of these problems. Do you want t to represent the actual year?
How about the difference in years?
Cool. So t could be years after
2006.
2006. So what data point then does this translate into? What data point is that?
080.
Okay, let me stop. Does everybody see that? So if we're the ones constructing the function, we have some control over what our variables mean. Right, so I'm not going to let t be the year. I'm going to let t be the years after 2006, which captures the change in time you're talking about. That's what really matters, is how much time has gone by. So in 2006, that's the beginning. So no time has gone by. So what data point is this? Somebody else tell me.
Six.
Yeah, 6 years later.
180.
180. I like it. Okay. So let me write down, here's the function we've got. So how do I use this point? What does that point tell me? In fact, let me make this better. There should be a t up here. Poor little dude. Oh, it should be, let me use all their variables. That's probably a good idea. Let me start over again. So we have n of t is going to be a times b to the t. Okay. I desperately want you guys. This is nothing major. What does this point tell me? This point tells me t is 0.
Plug it in.
Yeah, and n is 80. So n is 80 when t is 0. What is b to the 0?
1.
Crazy shit. So then what do I know? I know a is 80. So in general then, for this can be considered the initial amount in these kind of problems. That's the initial amount. Because when this is 0, then this will equal that because this part will be 1. So it's sort of like the equivalent of the y-intercept in a way, right? Okay, maybe. So now I know my function looks like this. So I still got to figure out what b is. So how the hell am I going to do that? What can I do? Do I know anything else?
The 180, you can plug that
I
in.
know this whole other point, right? And this tells me when t is 6, Jeff, there you go, buddy. When t is 6, the output is 180 for the number of deer. Poor little 8. You got a tiny little, never did leg day. There you go. Okay. Now, nobody say a word. Solve that for b. I'll wait. Solve that for b. Let me write it better. All right, solve that equation for b, please. I'm really curious if you guys know how to do the last step of this solving. What is that? 9/4, I think. So then what do I have to do to both sides to solve for b?
Take the 6th root.
Sweet. So b is the 6th root of 9/4. What is that? You guys know how to do that in your calculator?
I was going to ask, how do you plug a variable in for the root?
All right. There's actually a way to do it in the TI calculator a different way, but let me show you this. What's another way to write the 6th root of something? What's another way to write the 6th root of something?
X to the 1/6.
There you go. That's how you do it. You do 9/4 in parentheses to the parentheses 1 divided by 6. Jeff, I swear to God, man, I have not taken enough of whatever I need. Let's see. So if you put that in your calculator, 9/4 to the 1 divided by 6, that'll be the 6th root of 9/4.
It's roughly 1.145.
Yeah, and other stuff. What is it? 1.145. Yeah, sure. That's
Yeah.
Do. So they told me 2 pieces of information. Why does that make sense? How many parameters are there in this equation? There are 2 variables, the number of deer and the time after 2006. How many parameters are there? Do you guys remember what that means? It's the other letters that aren't really variables, right? So there's 2 of those. There's this A and this B. So if there are 2 things I don't know, how much information do I need? 2 pieces of information. So that's why they gave me 2 pieces of information. I really, really want this to make sense.
Would that have worked if b wasn't to the 0 power?
Yes, they could have given you 2 other points. This kind of problem, I can always make it the y-intercept that they give me, because I can always define it so that this first point is 0, comma something. But there could be a problem where they give you a point that doesn't have a 0 at first. And all you do is you do what we did here. You do it twice, right? You plug in 1 point's worth of information, you plug in the other point's worth of information, and you see what you can do. It'll still work. So what's our function look like now? Let me put it here. The number of deer would be, where'd it go? 80 times 1.145 to the t. Now let me, all right, well, let me see if I can make this. So this is kind of neat. I can tell this means that the deer population is growing by about 14.5% every year. That's a way to kind of break that thing down. Right, 1.145 is 114.5%. So every year this is growing by 14.5%. Did you have to know that for this problem? No, but I'm just letting you know that's where the growth rate comes in. Okay. You guys are really quiet except for 2 or 3 of you. So I'm really hoping this is coming through. Okay. All right, I'm going to clear all this away. Here it goes. Come on. So here, you guys do this one. Well, let's see what they wrote. Let's see what their answer was. Hold on. Blah, blah, blah. Well, they went one further out. I don't know why they went 4 decimal places. Did they say 4 decimal places? No. So screw them. Blah, blah, blah. And then they grabbed. Okay. So let's try. You guys try this one. I'll just sit here. Wow, 2 years. It went up to 237. That's pretty good. So wolves are. After this one, we'll try out example 5 because that's an example without the Y-intercept. It's just a Yellowstone? Do you mean that's what causes extreme population growth?
I was just comparing it to what happened with the wolves because they keep talking about populations and stuff.
Oh, yeah. Okay. Let's see. So just to make sure everybody's on the right track, can somebody who hasn't said a word to me yet tell me what your 2 points are that you're using?
Isn't it 0, 122, 129, and then 3, 236?
Careful.
Oh, 3. Oh, 2.
Yep, I like it. Good. Okay, beautiful. I really messed that number up, didn't I? Let me try to make that look better. Yeah. All right. All right, I'm going to start to catch up to you guys here. Do you notice how you really didn't have to do this first work? If I have the y-intercept, I know that that's going to be A. But again, I just did this to verify that again. Let's see. So this one will be a little bit easier, right? Nothing too weird here. Okay, who's got what B is? Anybody know what B is?
1.35.
Yeah, 1.35. We'll go ahead and give them another decimal place. Why not? 1.353.
Yes.
I like it. All right, so then my equation now, I bring back my N, I put my A in, and I put my B in, and then here's my T. So again, these are officially called parameters. They will change for different exponential growth situations, but they're not variables in the real sense. They don't change in a given situation. So N and T are going to change for any given situation. I really want that distinction made. So we have this idea of parameters, depends on the situation, and the variables depends on, in this case, what year am I interested in, right? How many years after am I interested in? Okay, so I think somebody just had this question a minute ago. What do I do if I don't have this point? This point seems really, really, really useful. So what do I do if I don't have that point? Well, first I panic. And then I stop panicking. So it's like this example 5 is exactly that situation, right? I'm going to erase all this here. It's going to go away. Here it goes. It's gone. Okay. So if I come down here. So somebody help me out. What am I going to write to get myself started here? What do you guys think I'm going to write? I should have erased the other stuff. I always start off with, let's see. No, I can't. So I really want you guys to understand.
The basic formula?
I'm not looking for a linear function. I'm looking for an exponential function.
Would
So
you write the basic formula of
Good.
the f of x equals abx?
I got to start with the model itself. And now I can throw shit into this, right? So if I put, so let's see, let's do this very methodically here. Let me erase this. If I put this point in, what do I get? I get 6. The output is 6 when the input is -2. And the output is 1 when the input is 2. Are you guys with me? I like it. Now, does anyone have a suggestion on what I can do next? There's a couple different things you could do. This very much looks like tell me, ask me, right? Have we done enough tell me, ask me for it to make sense when I say tell me, ask me? Can't I solve one of these two for a letter and plug it into the other one? Yes? So I don't care which one. Which one do you want to solve for a letter? Let's solve this one. Solve it for A. How do I solve that one for A?
Get A by itself.
That's true. That's what solving for A means. Now, how do I do it?
Divide by
Okay.
b squared or b to the negative.
Yeah, okay, I could divide by b to the -2, but do you understand how what's a better way to write 6 over b to the -2?
6
Using
times
the
b squared.
Like, yeah. So what's funny is I could have just multiplied both sides by b squared. Do you see how that would cancel that out? It effectively has the same result, right? But so now I know what a is. Now I know what a is. All right, so let me rewrite this. 1 equals a, but a is 6b squared. So a is 6b squared. And by the way, don't you guys remember systems of equations? What was one method you could use? Elimination or substitution? That's really all this is. This is substitution method. Solve for a letter, plug it in the other one. Right? So I replace a with what it is. And now I can solve for b because that's the only letter left. So 1 equals 6b to the 4th. So I get b to the 4th is 1/6. And then I've got to do some weird shit, right? b equals 1/6 to the 1/4. Is that everybody with me? Like, how do I kill a 4th power? I got to take a 1/4 power to kill it. I got to 4th root it. So let's see what we get for that. Have I lost anybody on a step there? I'm effectively doing the same thing. It's just easier when one of the points is the y-intercept. Everything is easier. Oh, okay. So somebody's got a question. Let me pull this up here. So 1 equals 6b to the 4th. Oh, crap. So divide by 6, divide by 6. So I get b to the 4th is 1/6. What do I have to do to both sides to kill the 4th power? I must take how do I kill the 4th power?
With a 4th root.
Yeah, I've got to take the 4th root. So I got to take the 4th root. I've got to take the 4th root. Do you have a 4th root button on your calculator? Not really. So what's the better way to write the 4th root? Is the 1/4 power. Now, I have this bad feeling that we're not as used to fractional exponents as we should be. Does everybody agree that the 4th root of b to the 4th is equal to b? Assuming b is positive. I mean, so don't come at me with any other problems. Okay. Watch this. You erased it, Jeff. No, all right. What happens with this? What do I do with powers in this situation? What am I going to do with these powers?
Cancel out.
Say again, sorry?
Are you canceling them out?
Yeah, because what am I going to do with them? What's the operation?
Multiplication.
Multiplication. So when I have something to a power raised to another power, I multiply. So like you just said, 4 times 1/4, my answer is b. So that's why the 1/4 power is the same thing as the 4th root, because they both do the same thing. They both accomplish the same thing. So they are both the same thing. I like it. This is something you might have done a long time ago. It's possible. It's been a while. So how do I rewrite the cube root of something? I rewrite that as x to the 1/3 power. And the way I remember it is, where are roots? Where are the roots on most plants? Aren't they on the bottom? So the root goes on the bottom because that's where roots are. And then I got my botanist coming at me with, well, actually, potatoes are roots and they're above the ground. Be quiet. Get out of here. but some tubers are actually, most roots are on the bottom. So give me a break. Okay, I like it. I'm not a biologist. All right, let's see. Man, this is all over the place. All right, but the main part of this problem is use 1 point's worth of information, make an equation. Use the other point's information, make an equation, and then solve one of them for a letter and plug it into them. It's a tell me, ask me thing. It's a system of equations. So we're just using substitution. All right. Let me clear this away. It's gone. It's going away. Wait, did we ever actually get to the answer? What would we, let me get the answer down here. So our function is going to be, what did you guys get for, let's see, what did you guys get for B?
0.64.
0.64?
Mm-hmm.
All right, yeah, sure. We'll see. And then what's A then? How am I going to figure out what A is?
Plug it
Plug
in.
it in, plug it in.
Yeah, 6b squared. So it'll be 6 times this squared. So I get about 2.45. You guys probably get something a little different. Let's see. Yeah, you guys probably got 2.46, didn't you? So let me show you a couple things. All right. So that would mean that our function is going to be 2.45 times 0.64 to the x. Okay. I'm going to erase all this. You guys ready? I'm going to erase all this. Okay. So let me show you something on the calculator. What you really got to get used to is not rounding things too early. So let me see if I can remember these numbers. Okay. There we go. All right. So when you do this, so you do 1/6 to the 1/4. I really didn't have to use parentheses, but too bad. So I get that weird number. Then how do I get the other letter? It was 6 times that thing. Have I shown you this yet? The ANS that has the last number that showed up on the screen in memory. 6 times the answer I just got squared. And there's your 2.45. Because if you use the rounded version of the number, I mean, to us, that looks pretty close, but that could be a huge difference depending on what the model is trying to be true for. Okay, maybe. All right. I know tonight's really exciting. I appreciate you all keeping your enthusiasm under check. Let me make sure I didn't miss anything else. I don't think so. No. Blah, blah, blah. Okay. And the nice thing is yesterday, I actually got a little bit ahead because the next section is all about graphing exponential functions, and they bring back the transformations. And we all remember transformations. We did some examples yesterday of transforming exponential equations. Now here's something that really gets dry. Here is the compound interest formula. This little dude right here, right? Has anybody ever seen this formula before? Does that look familiar to anybody? Nobody? Nobody? All right, let's do this. How much time do we have? Yeah, that's fine. Let's talk about this as a formula for a bit. Let me get off my ass. Let me turn off my dinosaur, which is a phrase I never expected, I would say, when I'm teaching, but there we go. All right. Let's talk about this for a minute. All right. I personally hate business. I am not a business person. I would never teach a business course. I might teach business calculus because I can handle that much business, but beyond that, screw it. So this is not exciting for me either, but I want to show you where this equation comes from a little bit, at least. And of course, all my markers are dying. Poor little dudes. So if I put, let's say I put $10,000 into a 12% account. Let's just pretend like there's a 12% account. Can you guys see all that? Yeah. All right. $10,000 into a 12% account, but it's compounded monthly. Does anyone know what that means? Compounded monthly.
Together.
Say again, sorry.
Put together.
All right. So okay. So you're trying to parse the word. So here's the thing. Simple interest, you would not make money on top of the interest you make each year, or each month in this case, or whatever. Compounded interest, they add the interest in, and then the next time they're going to add interest, it's going to be on that larger amount. So kind of like builds on itself. Okay. So what does that mean? So if I do this, it's a 12%. Whenever I give it a percentage, that's a yearly percentage. So I'm gonna compound this monthly. All right, what the shit does that mean, Jeff? So every month, I'm gonna do a part of this and add in some interest, add in some money. So let's do this first couple of months. Let's see what happens. So if it's a 12% yearly interest, how much interest will it be per month?
1%.
Holy shit. So after 1 month, how much money will I have in the account? Let's see. So every month I'm going to make 1%. How did you figure that out? Well, you took the rate and you divided by the number of times I was going to compound, right? It's not crazy. That makes sense. So how much money I'm going to have after 1 month? I'm going to have $10,000 plus how much? How do I figure out how much I'm going to add on top?
100.
Yes, you did 1% of 10,000. So that's 10,000 plus 0.01 times 10,000. 1212. So that'll be $10,100 after 1 month. Stay with it. So what's going to happen the second month? Same thing, except now I start where?
With the new total.
Yeah. So on top of the 10,100, I'm going to add 1% of the 10,100. So it'll be 10,100 plus 0.01 times 10,100. And 1% of 10,100 is $101. Really rolling in it now, right? So $10,201. And then it would keep going and keep going and keep going. So let me capture what's going on here. Let's call this, we'll call it P, and that stands for principal, right? P-L-E, not P-A-L, I believe. Don't hold me to that. Business and spelling. Who knows? This is the rate. We'll call it R. That's crazy. This is related to the number of times I'm going to compound. So we'll call that N. So in this case, monthly would be N is 12. If it was quarterly, it would be 4, of course, once every quarter. So that would be 4 times a year. So N is the number of times I'm going to add money in. How you guys doing okay so far? Trust me, I'm boring myself right now, but this is the math is neat, at least. Let's see if you guys agree. So how do I write what I've done here? It's P plus R divided by N times P. So isn't that factor of P out, isn't that this? Doesn't that represent what that is? Do you guys agree with me? So it's P plus, where did 1% come from? It was the rate divided by how many times I'm gonna compound this per year of times the principal again, that percentage of the principal. Let me stop for a minute. This is where it gets interesting to me. This is boring shit. This is neat shit. Now, what happens next? I'm gonna erase this because this is kind of gone past its usefulness. What happens next is this. This is where things get neat. So this is the first month. This is the first month. Oh, stay with me, guys. Oh, stay with me, guys. So the second month, I'm gonna start. How much money do I have now? I've got this much money. Stay with me. We're almost there. We're almost there. Trust me, we're almost there. And I'm gonna add this percent of that much money. So I have this much money plus that percent of this much money. So this isn't too crazy. It's starting to get, and you're like, good God, Jeff, don't go for the whole year, dude. Can I fit this shit in here? Yes. I'm going to be able to stop after this because then you'll see the pattern. I'm not going to have to do more than 2 months. Can you guys note, don't both of these have this in it? It's a GCF. GCF. I can take this out. So what's left? This divided by this is 1. This divided by this is R over N. So don't I have 1 plus R over N squared? So what about third month? What would this be?
Cube.
Cubed. I like it. So let's take a look at the book's equation now. So what do you think? So real quick, if I did this for 3 years, how could I figure out how much money is going to be in there? It'd be 1 plus R over N, not to the third power, correct? Not to the third power.
To the 36th.
To the 36th power, which is going to be N times T. That's the total number of times that I'm going to compound it over the whole life of the account. And that's basically the freaking equation, right? I mean, was that difficult? Some of you guys might have looked away and you missed out, and I'm sorry. I know it wasn't the most exciting thing, but it's not hard. It isn't hard. It's neat to go from this insane bullshit to this is beautiful. Look at that. Holy shit. Oh, okay. All right. So there's going to be a few problems where you just got to plug some stuff into the equation. Not that big of a deal. I just wanted to show you why that equation makes sense before you go start to use it. So let me just throw it at you one more time. There it is. Now you've lived through where that equation comes from. You should feel a little more comfortable using it. They give you some possible things. So annually, well, come on. I thought they give it. So if it was annually, N would be 1. Because it would be once a year. Semi-annually is 2, twice a year. Quarterly is 4, monthly is 12. Daily is normally considered to be 360 in a lot of business courses. I don't know what this book does for daily, to be honest. They might use 365. I don't know. All right. And this, all right, let's see. How much time do I have? Oh, this might be pushing it. All right, maybe next time. This is one of the most boring places where a certain letter comes into play. So you guys all know pi, obviously. You guys all know pi. Does anyone know a different, another letter that math uses besides pi? That's a Greek letter we use for a number. Is there another letter that you guys know we use for a number in mathematics? maybe related to exponential functions.
Is it sigma?
Not sigma. I think I heard somebody else say it. E. Yeah. So, all right. This isn't really, I'm kind of talking this down a little bit. This is not that boring, to be honest. This would say, now look what this means. This is doing it once a year, and then this is twice a year. This is 4 times a year. And do you see how much it's in? Obviously, the more times you add money in, the more money you'll end up at the end. So this is putting $1 invested at 100% for a year. I would hope that if you got a 100% return account, you would put more than $1 in, but okay, so let's pretend. So if I do it twice a year, 4 times a year, 12 times a year, daily, if I do it hourly, do it once per minute. So that's how many minutes are in a year. Look at this real quick. This is how many seconds are in the year. Isn't that roughly pi times 10 to the 7th? Isn't pi 3.14, and this is like 315 times 10 to the 7th? That's roughly, so that's a neat fact. Now you guys know there's roughly pi times 10 to the 7th seconds in a year. You're like, oh, good. Thanks, Jeff. I feel complete now. I understand. So what is happening is the more often I compound my money, the closer this gets to a limiting value. Do you see how it doesn't really change much down here at all? So if I just kept going, if I just kept pushing this number up to infinity, that would actually become exactly the number E. So the number E is like pi in the sense that it represents a number that has no pattern and doesn't stop. But this is the more boring place this comes from. So I'm going to tease something for tomorrow. Tomorrow I'll start class with the more exciting place. I mean, I'm probably overhyping this. It's a more interesting place where E comes from. I'll show you that tomorrow. I think otherwise we're almost done. Just to show you that we already did 6-2. This is going to be, come on, show me a good problem. Yeah, this is going to be with shifts. Here we go. There's your shifts. And I love how the book, every time it comes up again, they treat it as if you've never seen it before. But we've all seen shifts before. Who gives a shit? They work the same way. Up and down, left and right. Whoop-de-doo, book. We've seen it before. So 6.2 should not be an evil one. And yes, we do finally get into logarithms. Have you guys heard of logarithms before? Maybe? Yes, yes, yes. Okay. Do they suck? Do you know much about them? A little bit? All right. Hopefully, I don't know how much faith you have in me anymore, but hopefully I love logarithms. They're so much easier than I feel people think they are. So we're going to devote tomorrow to logarithms. That's where we're going to focus on. I'm going to show you how freaking easy they are is my hope. All right. All right. Otherwise, I think that's enough. Oh, shit. What have I done? There we go. Maybe, exactly. Do I still say that? Students have made fun of me. I say maybe. And I do this. I call this my hopeful Tai Chi. Hopeful Tai Chi. I'm as crossed as I can be. All right. All right, guys. You can head out if you want to. If you want to hang out, ask me anything, feel free. Otherwise, I'll see you all tomorrow.
Professor,
Yes.
actually, I have a question about the formula you just showed me.
Which?
The P time, yeah.
Oh, yeah. What's up?
Don't quite understand. Can you just explain to me again, please?
Explain the parts of it or explain where it comes from?
Yeah, where it's come from. The
Oh.
R, N, P.
Oh, what each part means. Is that what you mean?
Yeah.
Okay. So
Uh,
that's depending on what the actual question is. It's gonna.
Also, yeah, also like why, like on your back, it says P times like 1 plus. I think, can you use a whiteboard, please?
So
I couldn't get the part why the above, like P times 1 plus Rn times 1 plus that part, why it became that from.
oh, wait, let me see. All right. So do you see how this and this are in both terms? So I'm gonna right.
Yeah.
So I'm gonna take this.
Oh, fair. Yeah. Okay.
So this divided by this is 1.
Yeah. Okay.
And this divided by this is R over N.
Yeah.
Okay. And then of course I just collect those. Yeah.
Thank you.
Well,
Have a good one.
you too. Everybody else okay? I'm gonna head out. Yes, Charles?
Yeah, I had a question. On what homework is this? I think it's 5.6. Yeah, 5.6.
6, okay.
Question 77. It's the removable discontinuity. Yeah.
Yeah.
So, okay, so you factor out the top, right?
Yes.
And you get x plus 3, x minus 2. And the common factors of numerator and denominator, x minus 2. So obviously 2 is 1.
Sorry, say it again.
So x equals 2 would be the discontinuity,
Yes.
right? Okay.
So what's going to happen with this? So I always forget to do this example. What's going to happen with this? Normally there would be a vertical asymptote at 2. And the reason that would happen, so if it was just this, as x approaches 2, this would blow up. This would go to positive infinity or negative infinity because I keep dividing something by something that's going to 0. So it's going to go to infinity or negative infinity, correct?
Yes.
But if it has the same factor on the top and bottom, however small this gets just as small. So they keep canceling each other out. So it doesn't go to infinity. So the graph of this is going to look like x plus 3, but it's going to have a hole at 2. So it'd go up 1 over 1, up 1 over. There's going to be a hole right there. So that's why it's called a removable discontinuity, because all I would have to do is like fill it in like a pothole in the road.
Oh, okay. So that's where they got the 5. I got it.
Yeah.
That makes more sense.
I always forget. I get so invested in the asymptotes themselves. And then this is a really interesting thing that could happen if this is also up top. It doesn't let it go to infinity then, but it's still not allowed to be at 2. So it just sort of doesn't exist at 2, and then it keeps going.
Okay, so the removable discontinuity wouldn't be x equals 2. It's 2,
No, it is. Yeah, it
5.
is. Let's see. Yeah,
As
I
a
guess
point.
it depends on, I'm not sure of the way, but yeah, you could say 2, 5. There's a removable discontinuity at the point 2, 5, but you could also say there is a removable discontinuity at x equals 2. I mean, either way is an appropriate way to identify it, to be honest.
Oh,
2, 5 is
yeah,
more explicit, yeah.
Yeah, I looked in the back of the book and it said 2, 5, and I was like, uh-oh, I thought I did some bad math.
No. So that's kind of neat. It's like the line x plus 3 everywhere except at 2. That's the one place where it kind of freaks out.
Okay, and then I had another one on quadratic equations. So there's, I don't think it covers it in the book, but I have a supplemental book that I use that kind of just breaks down stuff.
Sure.
It says you graph the vertex and your x-intercepts. Okay, you have to select a point on each side. And it says use h minus 2a, h minus a. What? Hold on. I have it written down.
Oh, wow. That's getting way too. What is it trying to find?
So it sorry. Okay. So it says doesn't matter what points you choose to on either side, but a good rule of thumb is h minus 2a, h minus a, h plus a, and h plus 2a. And then
Oh, you
would
mean
just-
on either side of the vertex?
yeah.
Right. Now here's the nice thing here's the nice thing about that. If I give you, let's see if they have a quick one here. So we know the shortcut for finding the vertex. So that's gross. Let's see. Let's not do that one. Let's see. What's a good one? Let me just make one up. Yeah, because these are gross. Hold on. So if they give me this function here and I got to graph it. Let's see, minus, what do you want, Jeff? That'll be -2, so that'll be minus 16. Oh, let's do plus 7, sure, okay. Right, what's the y-intercept? So y-intercept. Yeah, y-intercept, I get it by letting x be 0. So what do I get when I put,
7.
7.
A 0.
I like it. Now, what's the vertex? Do you remember what's the shortcut to find the vertex?
That would be the b over 2a.
Yeah, negative b over 2a. So then it'll be -8 over twice 2. So I get -2.
Yep.
And then I plug it in to figure out the y piece, right?
Yes.
All right, just stay with me here. 8 times -2 plus 7. So you get 8 minus 16 plus 7 will be -8 plus 7 is -1. So you get -2, -1 is your vertex, right?
Okay. Yeah.
Now, to be honest, I've got all the information I need to graph a decent graph of this. And I'll show you what I mean. So I got the vertex is -2, -1. I picked a bad scale, but too bad for me. Right, the y-intercept is 0, 7.
Yep.
Vertex is -2, -1, so it's right there. And then I must have a mirror image of this. So see how this is over 2 and up to here. So I'm gonna have to have a one that's over 2 this way and up to 7. So I must have a mirror image point right here.
Yep.
So that's all I need.
Okay. So you don't actually need to have 2 other points between the vertex and the y-intercept.
Not really.
Right.
No.
Okay.
The only time you might need something is if if the vertex itself is the y-intercept, then you need something, right? But I mean, normally you just pick the next number over.
Okay.
You're getting later this semester, we're going to get deeper into parabolas, and we're going to talk about stuff like focal diameter, stuff like that. And that's where we're going to do something that sounds related to what they're saying. But right now, we're not that specific with it.
I see. Yeah,
So they might be
sometimes,
integrating like later stuff for us into right now, and we don't have to be that detailed yet.
alrighty, well, I appreciate it. Thank you.
Sure. All right. I'll see you tomorrow.
Yep. Bye.
How's everybody else? You guys there? All right, I'm gonna head out.